Assalamualaikum everyone. So for part 2, what we're going to learn is ICMP version 6 and also migration strategies. And you have learned before the ICMP for network layer in IPv4 protocol. Okay, so for this lesson, we're going to look also into the fragmentation in IPv6 and also ICMPv6 protocol. Okay, and migration strategies, right? So recall that in IPv4, fragmentations can be done at source as well as intermediate routers, but this is not permitted in IPv6. Okay, so in IPv6, routers do not fragment packets, and only the source can fragment in IPv6. So how the source wants to find out the MTU? Okay, it uses path MTU discovery technique, okay, which is mandatory for the source. Okay, using this technique, a source will find the smallest MTU supported by any network on the path. On the path means from the source to the destination. Okay, it will find the smallest MTU supported by any network on the path. So if path MTU discovery is not possible, it will send packet using the smallest MTU size. So for the internet, the smallest or the minimum size of MTU requirement is 1280 bytes. Okay, so that datagram will be fragmented to this size or smaller. This is in case that the path MTU discovery is not possible. Okay, so reassembly also done by destination node. Okay, so for this purpose, for the fragmentation purpose, okay, fragmentation offset and identification principle is similar to IPv4, even though these fields have been eliminated from the headers. It exists in the extension header. So IPv6 will use fragment header to indicate the next header, fragment offset, more fragments, okay, which is 1 bit, and also identification. Okay, as we can see here, this is included in the fragmentation extension header, not in the base header of IPv6. The code for fragmentation here is 44. It means that at the next header field, okay, we put 44 because it means that this datagram, okay, is fragmented. Okay, so fragmentation header here is part of extension headers defined in IPv6. Okay, so however, we have learned in details on how to fragment datagram using IPv4. So for IPv6, you just have to know just a little bit, okay, not into details for the extension header. Okay, so you can read that in the RFC documentation. Okay, so in terms of changes to other protocols, okay, when using IPv6, routing protocols also have to change because they need to handle new address format. Okay, before this, previously they handle 32 bits of IPv4 protocols, but for IPv6, they need to handle 128 bits, okay, which is much more longer. And also for the DNS in IPv6, they have added a new ACID resource record for A-type requests. Okay, basically these are some of the changes. There are many changes, okay, but I just highlighted some. Socket interface also need to be changed in terms of addresses. Okay, basically whatever applications or upper layer protocols that involve addressing, okay, then this need to be changed according to IPv6 address. And also for IPv6, UDP now requires checksum. In IPv4, it was optional. Okay, but for IPv6, UDP checksum field is mandatory. Okay, the maximum segment size in TCP also need to be recalculated, taking into account the maximum packet size of the IPv6. Okay, and any other protocols that handles IP address information such as FTP also needs to be changed based on the IPv6 address. Okay, let's have a look at the ICMP version 6. Okay, so in network layer for version 4, ICMP is one of the protocols that assists IPv4. Okay, that assists IPv4 in terms of error reporting. Okay, and for IPv6, it has similar roles to ICMP version 4, but somehow the ICMP version 6 has taken the roles of ARP and also IGMP in version 4. Okay, so in version 6, it is more complicated than version 4, and some protocols that are independent in version 4 now have been part of ICMP version 6, and there are also some new messages that have been added to make it more useful. Okay, so basically all the 3 or 4 protocols have been combined into one single protocol for ICMP version 6. Okay, just we look at the ICMP version 6 briefly. So like ICMP version 4, it is message oriented. It means that ICMP is used to report errors to get information, or to probe for neighbors, and also here to manage multicast communication. Okay, however, there are other protocols that are added to ICMP version 6 here to define the functionality and also how to interpret the message. Okay, so similar to ICMP version 4, for version 6, there are 2 types of messages, which are error reporting and also query. Okay, however, for query message in ICMP version 4, they only have echo, reply and request, and also timestamp request and reply. Okay, but for query in ICMP version 6, it has added group membership. Okay, group membership and also neighbor discoveries. Okay, so what's new in ICMP version 6? Okay, it is new in terms of functional structure compared to ICMP version 4. For error reports, okay, there is no source quench as is in IPv4. Okay, source quench, if you remember, it is used to control congestion in version 4. So it is eliminated in this version because in terms of congestion control, this has been taken care of by using priority and also flow level fields in IPv6 header. Okay, and redirection message move under query message. Okay, for the redirection message is in IPv4, it has moved under query message under neighbor discovery for ICMP version 6. Okay, there is also a new type of message added, which is packet too big. Packet too big is, for example, since IPv6 does not fragment at the router, so if the datagram is larger than the MTU size of the network, and that router receive that datagram, so 2 things will happen. First, the router will discard that datagram because the router, remember that router cannot perform the fragmentation. So because of that packet is too big and cannot go through to the next link on the network, it will have to discard the datagram, and then the router will send the ICMP error packet with the message packet too big. Okay, it is sent back to the source. All right. And echo request and reply, echo request and echo response message, if you recall, it is designed to check if 2 devices in the internet can communicate with each other. Okay, so in IPv4, the management of multicast or the group management here is given to the protocol called IGMP, or Internet Group Management Protocol. And for IPv6, this responsibility is given to ICMP version 6, okay, for group management and also membership. So it is a replacement for IGMP in IPv4, and it handles group membership, query, and for example, report and termination, which concern the group or multicast. Okay, and the next one is neighbor discovery. Okay, these 2 protocols are used by nodes on the same link for 3 main purposes. First, to find routers in the neighborhood that will forward packets to them. To find the link layer address of the neighbors, means to find the link layer address of the nodes attached to the same network. Okay, if you remember, in IPv4, this is done by ARP, okay, to find the link layer address of the neighbors. and also to find the IPv6 addresses of the neighbor. Okay, it is done through router solicitation or advertisement, and also neighbor solicitation, and also advertisement redirect. Okay, so the next one we will discuss on the migration strategies, okay, which is quite important because how will the public internet, for example, which is based on IPv4, transition or be transitioned to IPv6? Okay, the problem is that IPv6 can make it backward compatible. It means that it is designed so that it can send, route, and also receive IPv4 datagrams. Okay, so it means that IPv6 system can work together with the IPv4. However, the already deployed IPv4 system are not capable of handling IPv6 datagrams. Okay, so this is different. Remember, this is different. Like IPv6 is designed so that it can be made compatible with IPv4. However, how can IPv4, for example, works together with IPv6? Okay, so there are several transition strategies, and it calls dual stack, tunneling, and also header translation. So these approaches differ in terms of, for example, dual stack here provides complete implementations of both versions of IPv4 and also IPv6. Tunneling here provides a means to carry IPv6 packets over unmodified IPv4 routing infrastructures, and header translation is to enable networks to have IPv4 and IPv6 coexist in the same network or in somewhat rational manner while transitioning to an IPv6 network. Okay, so both dual stack and tunneling can be read further in RFC documentation 4213, and for header translation you can try to find it in RFC 6144. Okay, so this is example, the diagram of dual protocol stack, tunneling, okay, tunneling, and also translators. Right, so we will have a look one by one. Okay, so for dual stack, okay, nodes will support IPv4 and IPv6 at the same time. Okay, in other words, a node must run both IPv6 and IPv4 and IPv6 protocols simultaneously until all the internet uses IPv6. Okay, so the applications for these hosts also are supporting both protocols, and the network also can route both protocols. Okay, so to determine which version to use when sending a packet to destination, the source will send the query to the DNS to find which version to use to send a packet to the destination. So the decision is based on the DNS. So if the DNS returns an IPv4 address, then the source will send an IPv4 packet. And if the DNS returns an IPv6 address, the source will send IPv6 packet. And the node here needs to have the ability to send and receive both IPv4 and IPv6 datagram. So for example, when a node, IPv4 node, okay, interoperate with IPv6 node, so it can speak IPv6, okay, and vice versa. Okay, so both IPv6 and also IPv4 nodes must have IPv6 and also IPv4 addresses. Okay, must use both addresses. All right, so this is basically the dual stack. Okay, if you see in terms of the layer and the network layer, nodes are using both IPv4 and IPv6 protocol. Okay, so for the next strategy is tunneling. Okay, so tunneling provides a way to utilize an existing IPv4 routing infrastructure to carry IPv6 traffic. Okay, basically, when two computers using, if you see at this example, two computers are using IPv6, want to communicate with each other, and the packet must pass through a region that uses IPv4. This is IPv4 region. So the IPv6 packet is encapsulated in IPv4 packet. IPv6 packet is encapsulated in IPv4 packet when it enters the region, and when it leaves the region, it leaves its capsule. Okay, it leaves its capsule. Okay, so in other words, if you see here, the IPv6 node on the sending side will take the entire IPv6 datagram, puts in the payload field, okay? Puts in the payload field, all right? Puts in the payload field of the IPv4 datagram, okay? So basically this header and payload here is put as the IPv4 payload. And then this IPv4 datagram is then addressed to the IPv6 node on the receiving sides of the tunnel, okay? And let's say the intermediate routers here. The intermediate routers here will treat this packet just like any other datagram, meaning that they are not aware that this IPv4 datagram contains a complete IPv6 datagram, okay? It does not aware, or they do not aware that this is this IPv4 datagram have IPv6 originally is IPv6 datagram, okay? So the IPv6 node here on the receiving side will receive the IPv4 datagram, and it determines that IPv4 datagram contains an IPv6 datagram. It will extract this original IPv6 datagram, and then it can further route this datagram. If this is not destination, it can further route this IPv6 datagram to another IPv6 node. All right. So basically, this is tunneling. Okay, one of the strategies when two computers in the IPv6 system wants to connect together. However, they need to pass through IPv4 region. Right? So the final strategy here is using header translation. Okay, so header translation is suitable when the majority of the internet has moved to IPv6, but some systems are still using IPv4. So basically, this is not happening yet. And translation enables the client of a network, okay, to access the service of the network and communicate with other network users regardless their protocol usage. Okay, so for example here, the sender wants to use IPv6, but the receiver does not understand IPv6, so it cannot use tunneling. Okay, because tunneling is suitable when the sender wants to use IPv6 and it needs to send to another destination which also using IPv6. So for this case, the header of the IPv6 packet is converted to an IPv4 header, right? So this is, for the example here, IPv6 host, okay, with the header and also payload goes, this datagram are being routed, okay, in IPv6 region, okay. However, before it reaches destination, the header translation process will be performed here, okay, at the final router before it reaches the destination. Okay, so the header translation will be performed to translate the IPv6 header to IPv4 header, okay, before it will be finally arrive the IPv4 host, right? Okay, so basically this is all for IPv6 or for chapter 5. It is not too details, okay, because this is just like introduction of IPv6, okay, so that you know what is the difference, the main difference between IPv6 and IPv4, and you understand the addressing and also what cannot be done in IPv6 that can be done in IPv4 and vice versa, as well as the migration strategies on how to work between IPv6 and also IPv4. Okay, so finally you need to record your attendance here for chapter 5. This is compulsory. All right, so please scan this and fill the form to record your attendance for chapter 5 once you have finished watching 2 videos for chapter 5. Right, so thank you.